So in the first section of chapter 8, the way they begin is with an overview of these two things, and then we'll dive a little bit more deeply in the following sections, and then the fun will begin. So in the first section of chapter 8, we want to begin by introducing the idea of a sequence. So a sequence is basically a list of numbers. So you can think of them initially in the simplest format as just numbers being listed one at a time and usually separated by a comma. So a simple example would be something like if we had 2, 4, 6, 8, etc. So a sequence of numbers might be finite or it might be infinite. So it could be that you have a couple of dozen things in your sequence, or it might be that the list goes on forever. So if I put the little ... there, then that suggests that the sequence continues and it hopefully follows a pattern that's observable. So hopefully if you see some elements of a sequence like I've shown you here, you might be able to predict what's next, maybe or maybe not, depending on if you can recognize the pattern. Sometimes that's easy to do, sometimes it's not. Then if you have a ... it might be that that's followed up with the tail end of the sequence if the sequence is finite and ends somewhere, or it might be that it's not followed up by anything because the sequence continues on infinitely. So this first example that I've written here with 2, 4, 6, 8, ... suggests that it continues with that pattern on indefinitely. And if we could see that this is going up by 2 each time, or is positive even numbers, or however you want to think about it, then you might be able to imagine from this brief description that you know the whole thing, even though there's infinitely many things to know here. However, if, for example, the sequence had the ... and then had a finishing like this, by adding a couple on the end, this suggests that the sequence continued on the way it started, but up until it reached this ending point. And that means that this is a finite sequence instead of infinite. And you could even hopefully describe it as the even positive numbers less than or equal to 100 or something like that. So this is the idea of a sequence, that it's not only a collection of numbers, but they're listed. And so how is that different? So for example, if I just have some numbers without any ordering to them, then we'll usually refer to that as a set. So let's compare that. So take note, let's try this. So if I use a big curly bracket notation like this, then I could have items in a set 2, 4, 6, 8, 98, and 100. So if I have things like this where I have a set of numbers, our standard work up until now has suggested that the items in the set, the order of them didn't matter, and that it's just a collection of items. Even though to write some of them, you would kind of think you had to have some ordering because you write the first one and the second one, and that's naturally true, but it didn't actually matter to the set of numbers that you were describing. Whereas in a sequence, order does matter. There's a first item, there's a second item, there's a third item, and that's why I referred to this in the beginning as a list of numbers. So a list of numbers suggests that order matters. That the order in which the items appear is as important as the values themselves of the numbers. Whereas in sets, order doesn't matter. So any questions about that so far? Okay. So a sequence is basically any ordered set of numbers. And so let's introduce some notation so that we can talk about these, including referring to specific items or elements of the sequence. So the notation for a sequence is typically, whoops, I wanted to change color there. The notation for a sequence will be typically where you have an A with a little subscript of an N, and then this will then refer to the nth element of the sequence A. So, for example, in the sequence that we have above, A sub 1 is equal to 2, because that was the first item of the sequence written. A sub 2 was equal to 4, etc. So when you have a sequence, you can use an A or a B or a C, and they use these instead of like an X because these are constants. These are values that don't change. But the subscript allows us to refer to a particular element on the list in the sequence, the nth element, the first one, the second one, the 10th one, whatever. So what we can also see from this is that I could then, if I wanted, use this notation to write a formula that tells me how to predict a particular element on the set. So for example, the formula notation for our example would be that A sub n is equal to 2 times n. So when I say a formula, this basically means like a function, that you write a function expression that you can plug into the particular number for the position on the list. So this, since you have a first, second, and third item on your list, n would typically be a positive integer, for the 5 for the fifth item, 6 for the sixth item, etc. And that if you then say, if I want to know what the fifth item on the list is, I plug a 5 into the formula, and the formula tells me. So for example, if the formula is 2n, then I know the fifth item in my sequence is 2 times 5 or 10. And of course, we listed the first few items up here, so you could sort of predict if I was trying to go in here, all right, this is item number 1, this is item number 2, etc. But here you can see the relationship between the numbers down the sequence and the formula, and the numbers the position number and that you would plug into the formula to get the value on the sequence. All right, so let's try another example and see if this is making sense to folks. Let's do this the other way. Let's say I started by giving you a formula. So I'm going to use a different script for my sequence, so we know it's a different one. If I have B sub n, and in this case for B sub n, we're going to do 5n plus 2. So this is basically written like a little function. Little formula is like a little function. And so then we can ask, for example, what are, I don't know how that happened. What are the first 4 members or elements of the sequence? So then to figure out the first 4 terms, members of the sequence, you would plug in the numbers 1, 2, 3, and 4 in the formula and see what we get. So B sub 1 would be 5 times 1 plus 2, which is 7. Okay. B sub 2 would be 5 times 2 plus 2, which would be 12. I think I'm at the end of this page. There we go. And then if you do that for each of the 4 cases, you get the first 4 terms of the sequence, 5 times 3 plus 2, which is 17. So compare that by using the formula to find the terms of the sequence with the idea, if we had just given you the first 4 terms of the sequence and said that, what do we have? There we go. 7, 12, 17, 22, ... So the formula is nice because there's no guesswork. You simply plug into the formula to see what you get. And then maybe afterwards you can kind of recognize the format of the pattern, 7, 12, 17, 22. However, it's also nice when you have the first few terms written out immediately, because then you can kind of see the sequence as it lives, meaning you can just see the numbers and how they sit beside each other and if they form a pattern. And in simpler sequences, this is probably quickest and easiest because in this case, you can see you started with a 7 and then you just added 5 each time. Questions so far at all? Okay, so let's do this. Let's look at an example for the book and introduce the next concept. So I'm going to erase the page I have here so that we can start fresh. So let's consider too many dots. So I'm looking at example 3. Uh-oh, lost my screen here. Hang on. Here we go. On page 598. So it says, consider the following sequences. So looking at part A, it shows, okay. All right. For some reason my pen is drawing more than I want it to. It says A sub n is equal to -2, 5, 12, 19, ... So here they're telling us that we have a sequence and they're using this A sub n notation. And when they put the A sub n in the curly brackets, that's how we know that it's a sequence instead of a particular term. So the curly brackets mean here is the whole sequence, and then they've tried to give an equivalency or tell us what it's about by just showing us the first 4 terms of the sequence. So the goal for them to just get used to this notation in example 3 is to find the next 2 terms of the sequence. So in part I, we want to find the next 2 terms that would follow. So anybody who wants to speak up, see what they believe the pattern to be in this sequence?
It's addition by 7.
Addition by 7, sounds good. So then we could use that pattern recognition to move forward to the next two terms of the sequence. So I could also use our trying to gain comfortable with the notation of a sequence to try to predict what's coming. So since they've shown us the first four terms, they're asking for the fifth and sixth term. So I could write a sub 5 to say what the fifth term would be. So a sub 5, if we added 7, would be 26. And a sub 6, if we add 7 again, would be 33. So then in part 2, it says, find a recurrence relation that generates the sequence. So a recurrence relation is a way that we can observe how you get to the next term in the sequence from the previous one, how the step is taken. This is sometimes also referred to as a recursive definition. So the description that was given was that the way you get to the next term in the pattern is to add 7. And so the way I would annotate that is something like this. You can write that the next term in the sequence, and this is written as a sub n plus 1. And so I'm referring that as to the next term because normally we use a sub n to refer to a particular term. So if I add 1 to n, then I get the next term. And then what you give with a recursive relation is you show how the n plus 1th term would be arrived at using the previous term, using the nth term. So I could write in this case that that would be the nth term plus 7. So this is referred to as a recursive formula, or as the book recalls it, we're finding a recurrence relation that generates the sequence. So this basically says that every time you have an nth term, the way you get to the next one is you add 7, and then you just keep going that way. So then in the third part of the example, it says find an example formula for the nth term of the sequence. So now that we know how we get from one term to the next, and we know where the sequence starts, we're in fact given the first 4 terms of the sequence, they want a formula for a sub n. And so what we have to do in this part of the problem is use the fact that we know how you get to the next term, that 7 is added each time, and that the first term you started with was a -2, to figure out how to write what the nth term would be. For example, what would a sub 3 be? How would I get that 12, the third term in the sequence, using a formula, as we talked about before, having a formula definition for the sequence. So we know we start with -2. So I'm going to write the starting value of -2 here. And then the question then to figure out how to get the nth term would be, how many times did we add 7 to get to the nth term? And so, for example, in this case, in the first term, you have your -2. You didn't add any 7s at all. So I'm going to annotate that up here. So up here, we have a -2. And we're adding 7 as we move each time, but in the beginning we haven't moved, so I've added 0 times 7. In the next term, we have -2. We started with a -2, but then we added a 7. To be in the third term, we have -2. And we added 7 to get to the second term, and then we added 7 to get to the third term. So basically, each term in the sequence, we've added 7s to get there from the start, but the number of times that we added 7 is 1 less than the position we're in. To get to the third term, we added 7 twice. To get to the fourth term, we will have added 7 3 times, etc. So it looks like I can see people are giving me indications that people are trying to put in a chat, but it's not showing me them when I'm on a shared screen. And that's something I have, figured out. Let me try this. So chat, says chat. So if I open up the chat, there it is. Okay, so yeah, I got the chat box here. All good. So I see the +7, a sub n equals 7 times n minus 1 minus 2. So that's nice from the formula. Thank you, Marcus. That's exactly right. Okay, so I definitely like that this is coming easily for some of you, since especially the format of delivering the material this way is challenging. And I'm trying to make it as clear as possible, since it is a little harder to interact with folks. And if that means that you see the answer before we get there, that's great, good for you. And that means I don't have to worry about you. All right, so again, what we can see here is that basically the way you make a formula for the nth term in a sequence, when you're working with just the first several terms, is to try to see what the pattern is, and then predict what the formula would be that would follow the pattern and land you on the nth term. And one of the things to keep in mind about being in the nth position on the sequence is that the number of times you've moved position from the first term to get there is 1 less than n. So for example, to be in the 4th position of a sequence, that's 3 terms after the first one, or 3 elements after the first one. So in this case, as we're seeing in the 4th position, to get there, I would have had to add 7 onto our starting value of -2 3 times. So if I go down to the explicit formula I'm trying to write, then it would be -2 plus 1 less than the position I'm in, which is n minus 1 times 7. So if I was in the 4th position, I would add 3 times 7, because I would have added 7 3 times. And more importantly, if I want to predict out down the line and say what the 50th position would be, I would take a -2 and add 49 sevens by multiplying 7 by 49 and adding that. Again, this is all on page 598 for those who are trying to follow along with the book with them. So questions about that? Okay. So that was example 3 from the book. And we're trying to basically get used to the idea of working with a sequence of numbers, as well as the notation we would use when doing so. So let's introduce the next concept. Well, we've been working with a sequence of numbers in calculus back since the beginning first chapter 2, because that was the initial introduction to the idea of a limit. So for example, let's say we had a sequence a sub n, and let's say we had 0.9 as my first term, 0.99 as my second term, and so I have 0.9, 0.99, 0.999. So you can imagine that we can have a sequence of values, and then we can ask the question, or try to determine what is the limit as n continues on in the sequence of a sub n. Actually, that's not the right notation. So this puts us in a position of evaluating limits as we had before. And if you have a formula that expresses the nth term in the sequence, then you could literally just take the limit of that formula as n goes to infinity. And then that would just be a limit problem. Now, you may recall that our normal sense of using a limit is that sometimes you're approaching a specific value, like the limit as a goes to 5 or something like that. and you're imagining inserting numbers very, very close to 5, like 4.9, 4.99, things like that. Whereas in this case, for a sequence, we'll be looking at the limit as n goes to infinity. And as n goes to infinity, of course, it's following just integer values. It's following whole number values, 1, 2, 3. What's that, Joseph? Question? No? Okay. All right. So for this case, just from our understanding of limits, do we think we could see what the limit of this a sub n sequence would be?
Would it be 1?
Yeah. Okay, so then in this case, we could say the limit of this sequence is 1. And if we had a formula for it, we could try to figure that out as well. But let's look at another example from the book. So this is example 4. So let me point out that in the book, the definition of the limit sequence is of a sequence is on page 599. And just as it was with a limit, basically the limit L of a sequence is the value that it approaches in a limiting fashion. Basically, the limit as n tends to infinity of a sub n is L, then we call that the limit of the sequence. But let's look at another example here. So let's see, this is which one? Example 4, let's look at part A. So it says, write the first 4 terms of each sequence. If you believe the sequence converges to some limiting value, make a conjecture about its limit. If the sequence appears to diverge, explain why. So again, they're not asking for anything too formal here, but to make a conjecture, which is an educated guess. So let's look at the first one. And this will also stress our notation a little bit. So it's -1 to the nth power divided by n squared plus 1. And they've used this notation where they say n equals 1 to infinity. So a couple of things to point out about this, this notation. This is another example of sequence notation, but instead of inside of the curly brackets writing a sub n, they just replaced a sub n with the formula for a sub n in the nth position. And then, because as I mentioned before, a sequence might be finite or infinite, they've put a starting value for n on the bottom, and then they've put the infinity on the top here, similar to the limits we put in when we're evaluating a definite integral or something like that. So again, this is just a notation to try to communicate a particular sequence and how far the sequence goes, but it's something that, as usual, we still have to get used to. Questions about that notation at all? Okay, so it says to write out the first 4 terms. So again, to get used to using the notation, you would write something like a sub 1 and then figure out what that gets. And to get that, you would plug in a 1 into the value of n using the formula and see what you get. So that would give me -1 to the 1 power up top over 1 squared plus 1, which is -1/2. Similarly, if I plug in a 2, if I square the -1 up top, it becomes a +1. And if I square it on the bottom and get a 4 and add 1, I get 5. So I get +1/5. And so using this pattern, let's just write out the first 4 terms. So we'd have -1/2 followed by +1/5. And then if I plug in a 3, I get a negative on the top again. And then on the bottom, 3 squared is 9 plus 1 is 10. And if I plug in a 4, then a -1 to the 4th power, since that even goes positive again. And on the bottom, I get 17. So there's the first 4 terms, and then it just continues on like that. Questions about that? Okay, so just warming up to the notation. Initially, just determining terms of a sequence when you have a formula for the sequence is great. That's not too hard. So then but then it asked us to make a conjecture about whether this has a limiting value or not. So you can imagine trying to take the limit in the formula. You can imagine trying to look at the terms of the sequence and see if you see enough of a pattern to predict where they're going in the end or in the long run. And again, one of our options is that it diverges, meaning it doesn't settle on a value, that the limit doesn't exist. So anybody want to ask a question about that or think about how you determine if this is settling in on a value? Let's back to the concept of a limit in chapter 2. What do you guys think?
From the pattern, it doesn't seem that too much that it's settling on one value, but I think we may be able to check if we take the limit of the formula.
And so what would be your thoughts on how to take that limit? Like if we look at this formula here. So if we're looking at that formula and you're imagining that we're going to take the limit as n tends to infinity, what comes to mind there?
Let me see. Well, if I plug in, or if I, let's see. I feel like with the bottom just zero out. In this case, if we take one.
Anybody else want to think of a question or chime in with an idea?
Would you be able to use L'Hopital's?
So it is interesting. All of our work that we'd like to use before never really had functions that just have discrete values, meaning you're just plugging in whole numbers. They were always continuous and things like that. And so you could imagine that we could ask ourselves, what if instead of just being something where I had to plug in whole numbers like 1, 2, 3, 4, 5, 6, could I treat this like a function of x? Then I could try to imagine using L'Hopital's rule. So all of our previous work wasn't something like this, but it seems like it's applicable. So here's the comparison. Compare to the limit as x tends to infinity. So how could I imagine trying to replace this with an x? So here's why we have a little trouble with things like this. The numerator is -1 raised to a power. And so I could write that as like -1 to the power of x or something, but typically all of our work with exponential functions, the base has always had to be non-negative. The base has always had to be some positive number. You can do individual arithmetic, but as soon as you try to use a negative number as a base of an exponent, then you have problems because fractional exponents on negatives are undefined in the real numbers. So it ends up being kind of complicated. So the first thing you could imagine is you could say, all right, what if I just ignore the -1 power thing on the top and I take the limit as x goes to infinity of 1 over x squared plus 1. So let's say we started considering this as a comparison. So obviously that's not exactly what we have in our formula here, but it's something we can think about to see if we could have some ability to get an idea of what's going on. So is that something where we would know what the limit is, or we could use L'Hopital's rule if we needed to? What do you guys think?
that become undefined?
So why are you thinking undefined?
I was just thinking if we have a small number over an increasingly large number, it tends to 0, right?
And does that make it undefined?
No.
So what's your new conclusion?
That it tends to 0.
Yeah, exactly. So this is our classic, the bottom of the fraction is becoming huge. So you're getting like 1 over 10, 1 over 100, 1 over 1,000, 1 over a million, 1 over a billion, which is shrinking away to nothing. You can also just imagine as a function, it's basically like 1 over x squared, which settles down to the 0 x-axis. So this is going to be the kind of thing we're going to be considering a lot during this chapter. It's going to draw a lot back onto previous limit problems and concepts. And so and we're also in a situation because of the sequence formula that we have there, but that sometimes it's kind of hard to figure this out directly with tools from limits before. So you might really want to be considering exploring some of these graphically or even numerically, just plugging in some numbers that are large and seeing if you can determine if it looks like it has a limiting value. So yes, the limit as x goes to infinity of 1 over x squared plus 1 is 0. So this is equal to 0. And the way to think of that is literally that the bottom is tending toward an infinity while the top is just sitting there as a 1. And if you divide 1 by a larger and larger number, the resulting ratio shrinks away to nothing. So now the question is, are these numerators of an oscillating 1 and a -1 going to change that? Because we looked at this limit by ignoring this thing on the top, because if I put a -1 to a power of x in the top, then all of a sudden that's not a continuous function and all of our ways of thinking about limits before can't be applied. But if we put that back in and we imagine a number on the top that's oscillating between a 1 and a -1, we could then ask ourselves, how would that affect the result? Any thoughts, suggestions? Okay, so they actually, of course, draw a nice picture in the book that might make this a little bit more clear. So if you, I would say, see the figure 8.3 on 599. So let's put that here. Oops. But I'll try to draw just a little brief sketch of it. I'm referring it because I just don't think it's going to come out very good in this format. It comes out bad enough in class. So they're basically saying that you should think about this graphically. So if you're considering the formula for our function and you start to graph points, we could see that we have the first 4 values of our sequence here listed. So you could imagine that these are occurring when you have like 1, 2, 3, 4. And so if I'm up at a 1 up here, for example, that I'm initially, and then we're going to say maybe down here somewhere is -1, that I initially have a value of a half, and then I had a value of positive 1/5, and then I have a value of -1/10, and then positive 1/17. And so what you can do is you can see that the values, even though they're oscillating between being positive and negative, they're going above then below the axis, that if you considered either set by itself on both sides, you have a function that's shrinking around down to 0. And with the idea of a limit, that means that as x goes off toward infinity, this gap here, but both the values above or below go to 0. And therefore, the limit of the entire sequence is going to be 0, because you can make the value of the expression get as close to 0 as you want by letting n be arbitrarily large. So there's no way to do that algebraically. So this is a purely graphical, numerical, or analytical problem. And again, never sure how people's comfort with the idea of limits exists. So maybe some of this work up here will try to give you some memories of imagining when you have the dynamics of a function. If the top is a constant and the numerator is becoming huge, then the fraction heads to 0. Questions, comments, discussions about this example 4a? Okay, let's take a look at B. So B, they give us another explicit formula. And we have the cosine of n times pi. And like before, this is as n starts with the first term and goes off toward infinity. So this is an infinite sequence, and I just have to try to make that better. Yeah, maybe. Okay, so like with before, we would want to say what are the first 4 terms. So if n is a 1, then I have cosine of pi. So what is cosine of pi?
-1.
Yeah. So then when n is a 2, we have cosine of 2 pi, which is back to a 1, right? So then we have cosine of 3 pi and cosine of 4 pi. So what we can see in this sequence, just by doing the first few terms, is that it's just oscillating back and forth between -1 and 1. And this is probably a good time to try to have you focus on the idea of recognizing that even when they give you the sequence by using a formula, and maybe the formula, even as in this case, has a function in it, right? Compare this to just the formula like cosine of, actually, where normally n is our variable, compare this instead to if we had the cosine of pi times x. So if I have cosine pi times x, we have a continuous function. We can imagine that it does its little bumps up and down, and it's periodic, and everything that we're used to thinking about with cosine. But when we have a sequence, you only plug in whole number values, and then you get a sequence of values that result that aren't connected to each other. So in this case, this sequence are just 1s and -1s. There's no intermediary values. This never is a 0, right? So this is not a function the way we're used to thinking of a function. It's just numbers -1 and 1. And in this case, they alter. They take turns. They oscillate. Questions about that at all? Okay, so again, we're supposed to make a conjecture about a possible limiting value or a possibility of divergence. Any thoughts about that in this case? So in the end, you kind of have to ask yourself, if I allow n to get bigger and bigger and bigger, does this sequence of answers settle in on a value or not? So do we think just going back and forth between -1 and 1 over and over and over again will get infinitely close to a particular number?
No, because it's just oscillating for infinity, right?
Yeah, it just keeps doing this forever. And so we have to remind ourselves that the concept for a limit is that the farther you go, the closer and closer you get to one specific particular value. And so since this never zooms in on or settles in on a number, then we would conclude that this is divergent, or that it diverges as a sequence. So I did sort of mention this briefly previously when we were looking at the improper integrals, that we're going to be using these words converges or diverges throughout chapters 8 and 9. And so we're starting to see that come into play here as just a way to say whether the limit of a sequence exists or not. If it exists, then we say the sequence converges to a value. If it does not exist, we say it diverges. So diverging does not have to mean going off toward infinity or something like that, even though that may be the case. As in this case, it doesn't go off to infinity, it just refuses to settle in on a value. It just keeps going back and forth between 1 and -1, and we still use this term that it diverges. Questions about any of this so far? Okay, I'm going to erase this. And let's start to talk about our next big topic, still in 8.1. So now let's say we have these possibility of a sequence in mind. And again, a sequence might be finite or it might be infinite. So then the next thing to talk about is series. So a series is basically the sum of terms or elements of a sequence. So let's say that A sub n is equal to, let's do it this way. Two, 4, 6, 8, 10. So in this case, I've given you a finite sequence, and I've given it to you by just explicitly stating what the sequence is. It has 5 elements or terms of the sequence. So then if I wanted the series for A sub n, I would add these up. So then you could write this using our summation notation. If I take the summation, in this case, we'll say as I goes from 1 to 5 of A sub I, using notation back from when we did integrals and things like that, or when we were doing volume problems and doing Riemann sums. Then this would simply be 2 plus 4 plus 6 plus 8 plus 10, which is what, 40? So this is an example of a finite series. Questions about that? me find a definition somewhere. They don't seem to have a box for it, so they describe it on page 601. Page 601. Okay, so again, we want to have some notation of some sort. So we typically use like the lowercase a or b or c to represent definition terms for a sequence and things like that. And so we'll usually use a big capital S with a potential subscript to refer to this sequence. So I would, in this case, I could say, let's do it. Yeah, let's do this. So there are 5 terms of this sequence. I could write S sub 5, and that would mean that the 5 terms of this sequence added up to 40. So the first thing to be clear about, just conceptually, is that when you refer to a sequence like a sub n, it is a list of numbers. It is an ordered collection of numbers with a first and a second and a third that may be finite or infinite. When you refer to a series, ideally, it's a result of a summation. So a series might be a number if you add the terms up and you get some result, or you might say that the series diverges if you don't get a number. Well, we'll have to look at that in a second. I'm getting ahead of myself a little bit. All right. So let's, let me just make this sort of explicit. S, oops, that didn't work. S sub n is the sum of terms of a sequence a sub n. Now, as we're using this notation, you can put in a specific value like this, or you can leave the value as a variable. And if you put in a specific value, then you're saying I'm adding up the first 5 terms of the sequence. And if you don't put in a specific value and leave it at n, that means you add up all the terms of the sequence. If the sequence itself was finite, then you're adding up a finite number of terms. If the sequence was infinite, then you're trying to add up an infinite number of terms, which may or may not have a limiting value or not, which we've talked a little bit about, for example, like getting the area under a curve of for an improper integral or something like that. So let's look at finite sequences with an example or two before we look at what happens if the sequence becomes infinite. So for example, let's try another example here. So let's say I had a sub n was equal to, and we'll do this with a formula, n minus 3. So in this case, this is potentially an infinite sequence because I haven't put any restrictions on the value of n. And then I could say that my goal is to evaluate S sub 5. So S sub 5 means a sub 1 plus a sub 2 plus a sub 3 plus a sub 4 plus a sub 5. I think I'm running out of space there. So in this case, S sub 5, we could then figure out what these first 5 terms of the sequence are and then add them up. So when n is a 1, we get -2. When n is a 2, we get -1. When n is a 3, we get a 0. When n is a 4, we get a 1. And lastly, when n is a 5, we get 2. So we're going to, this is called an example of a partial sum. So a partial sum is where I don't necessarily add up all the terms of an entire sequence, but I just add up to a particular specified value of n, in this case 5. So this partial sum gives me a number, I assume. -3 and 3 is 0. Oh, that was interesting. Didn't plan on that. So here we have a partial sum is equal to 0. We could, for example, consider s sub 6. So that would be to add up the first 6 terms of the sequence provided. So note, if I already have the result of the first 5, then to get the 6th partial sum up to the 6th term, I would just need to add what the 6th term would give us. So using the pattern here of our terms up above, if the first term is -2, then -1, then 0, then 1, then 2, what would be the 6th term? That would be 3. So what we can say is that instead of adding all of these up, these all added up to 0, right? So then this would be what we had with the first 5 terms plus the 6th term, which would be 3. So the thing I'm trying to point out here is that s sub 6 is equal to s sub 5 plus a sub 6. It's the sum of the first 5 terms of the sequence plus whatever the 6th term would have added to the list. Questions about that? So definitely hard for me to gauge the room. It's hard to see if people are following along. We've had a lot of information introduced. Let's just pause here and let's just see if we can take any questions about anything we've discussed so far, if people are willing to participate and chime in. Can anyone think of any questions?
Yeah, Professor. I had a question, but it was related back to series, though. Sorry,
Sure.
it was related back to the sequences.
Yeah, great.
So I was trying to figure out how we figured out the formula from the sequence itself. I understood that we figured out a pattern, and then it was just whatever you started from plus what the pattern would be to get the a sub n value.
Well, basically the example that we had, we were adding a 7 every time, right?
Right.
And so then we were saying you would have had to have done that, 1 fewer times than the position you landed on. To be in the 5th position, you added 4 7s or something like that. So for that particular pattern, we use that formula. In general, to find what the formula would be for a sequence, you basically have to figure out what's going on with what the book referred to recursively, meaning like how did you get from one number to the next one, and is that consistent every time? So it could have been that instead of adding 7 every time, that you multiplied by 5 every time, whatever it is. So then the formula will end up being taking the first term of the sequence and then doing to it whatever you're doing recursively in each step n minus 1 times. Does that make sense?
So it's n minus 1 because
to get to the second term, you've done it once to the first term. to get to the third term, you did it twice, once to get to the second and then again to get to the third. Let's say I tried to write that just sort of conceptually here. Okay. So imagine that you have, a sub 1, and then you have a sub 2, and a sub 3, and a sub 4, right, etc. And we could separate these with commas because this is a sequence. So if you have some pattern as to how you're getting to the next term, then each time you move to the next term, you apply something in order to get there. So it could be that in each of these steps, you added 7, or that you multiplied by 2 or by 5 or something like that. Does that make sense?
Right.
Okay, so notice that by the time you're at the fourth term, you have done whatever it is you do 3 times. So the number of times you apply the change to the number that gets you to the next number lags behind the position of the number by 1.
Oh, I see. Okay, that makes sense.
Is that helping to see that?
Yeah, that makes sense.
Yeah, so when you're at the fourth term, whatever you did to the first term, you have now done 3 times. So if you're adding 7, then you would add 7 3 times, which is the same as adding 3 times 7.
Got it.
If you were multiplying by 5, so let's say each time you do this, as another example, well, let's say you're multiplying by 3. That would mean that a sub 4 would be equal to a sub 1, and then you multiplied by 3 times. So that was times 3 to the third. Or in general, if I want to go to the nth term, then I start with the first term and I multiply by 3 n minus 1 times, which ends up being an exponent. How's that?
Got it. Yeah, that makes much more sense. Thank you.
Yeah, you'll definitely have quite a few problems in the problem set where you're trying to come up with what the formula would be based on observed terms and a pattern, which is very good because that's kind of like real world examination, seeing some values in the real world, trying to see if there's a pattern in them that you can then express with a formula. Sounds like a word problem. Other questions at all so far about anything up to this point in talking about series and sequences? Okay, I'm going to clear this page. Okay, so now we have a notation where maybe I have a sub n, and if I put it in some curly brackets, then I'm referring to an entire sequence, which may or may not be finite. And then I have the notation s sub n, and that refers to adding up all the terms in the sequence of a sub n. And so since a sub n might be finite or infinite, s sub n might be finite or infinite. So we can have a finite series, as we just looked at an example of, with like 5 terms or 6 terms, or you can have an infinite series. So when we have an infinite series, then we are looking at the idea of whether that can actually result in a number or not. So let's look at one I was referring to before. Let's say that a sub n, so here's an example. Let's say that a sub n is equal to um, 0.9. 0.09, 0.009. That's going to be a comma. And then I'm going to do one more, 0.009, and then go dot, dot, dot. Okay, so I've tried to write out an example of a sequence. We have a sequence of numbers, and you could write even a formula for the sequence of numbers. So let's show that you could do that. So even though I've written out the first 4 of them explicitly and then put dot, dot, dot to suggest there's a pattern, we could try to say, what is that value? And what we'll see is that you have a 9 in a position of the decimal number that keeps moving farther and farther to the right. So how could I write that? I could write that as 9 times 10, since in the decimal system it's based on powers of 10, where in the first position you're in the 1/10th place, in the second position you're in the 100th place, in the third position you're in the 1000th place. So that means this is 10 raised to the power of minus n. So this is a formula for the nth term in my sequence. Questions about that so far?
I have a question. So why would it be? Why would the exponent be negative?
Because let's see if I put it up here. When you have the decimal after the decimal, you're not talking about 10, 100, or 1,000. You're talking about a 10th, a 100th, or a 1,000th. So this is like 9 times 1/10. This is 9 times 100th. This is 9 times 1/1000. And remember, when you have a negative power, that's 1 over the number to the positive power. So if I have 1 over 10, or 1 over 100, or 1 over 1,000, those are 1 over powers of 10. So the first number is 9 times 1 over 10 to the first power. The second number is 9 times 1 over 10 to the second power. That means in general, I have 9 times 1 over 10 to the nth power, but to divide by an exponent makes the exponent negative if you write it without a fraction. Does that answer your questions, Yellow?
Yes, yes, it does. Thank you.
Okay. Okay. So this is an example of infinite sequence. So now we can ask ourselves, what is the infinite series? So we can just look at this sort of by definition and then consider it numerically. So this would be equal, if I were to sort of try to write it out, as 0.9 plus 0.09 plus 0.009, etc. So in the same way that I can put sort of these ellipses, this dot, dot, dot at the end of a sequence to say that the sequence continues in this pattern, you can put a dot, dot, dot at the end of an initially described summation, an initial series, saying and that the addition problem continues on in this way. Because what is an infinite series? It's a sum of infinite terms of a sequence. And so since the sequence goes on forever, so would the sum. And so the way we approach this and the way we think about it is you basically imagine adding them along the way and getting an accumulative total. So as I referred to before, we could then consider what's going on here by saying, well, what are the first two terms add up to? And then what if I then add the third term or the fourth term or the fifth term? And I keep going like that. And adding the first set of terms is what we referred to as before as a partial sum. So let's say we consider the increasing, meaning increasing in index value, increasing partial sums. S sub 1 would be the sum of the first one term in the sequence would be 0.9. S sub 2 would be 0.9 plus 0.09, which would be 0.99. S sub 3 would be the previous total, 0.99, that's S sub 2, plus the third term in the sequence, which was 0.009, which would be 0.999. So in each successive term of the partial sum, we add another 9 in the next decimal position down the way. So that means S sub 4 would end up with 0.9999. S sub 5, we'd have 5 nines. So then the idea is that the value of the series would be the limit of the partial sums. So if I want to refer to this series, I basically need to take the limit of these. So let's annotate that just to try to describe what I'm talking about. And then we can try to evaluate. I think I ran out of space here. Let's go down. So then you can think of it as the overall S, the sum, would be equal to the limit as n tends to infinity of S sub n. That would be the result if there is one of this infinite series. So what happens if we take the limit of the resulting summation that we're getting here? Can we see that numerically? Anybody have a suggestion? I haven't lost you.
Seems to be approaching 1.
Yeah, so goes back to when we were considering limits numerically, right? That you sort of say, what is a sequence, what's approaching 1, like 0.9, 0.99, 0.99, 0.999, and those are values that are getting infinitely closer to 1. So in this case, this should be a 1. So if you go back to the original sequence that we were looking at, then you could go back here and then say, okay, if we had this sequence of terms, and then we add all of those up, we get a 1. So we can literally imagine this infinite series as being S sub n was equal to 0.9 plus 0.09, and I'm going to not try to write it all again, and that this actually just equaled 1. Questions, comments, discussion so far before we look at another example? Okay, So let's pull an example from the book and see what we think about it. Oh, actually, this is an example in the book. This is their number 7. So let me just label that. So this you can find as example 7 on page 601. Go down again. Okay, so I'm going to pull then another example from the back, perhaps. Okay, so I'm going to take on page 606, this is from the exercise set. I'm just going to grab a problem. Exercise '74. And it gives us the following. So they will often refer to as series using sigma notation, since that way they can show you that things are being added, because this is the addition notation, and also they can give you the formula of the terms of the sequence. So this is what it gives us in 74, and the instructions are, consider the following infinite series, and then do 2 things. A says to write the first 4 terms of the partial sums. First 4 partial sums. And then B, it says estimate the limit or state that it does not exist. Estimate the limit of the sequence of partial sums, or state that it does not exist. D and E. Okay, so in part A, the first 4 partial sums means find S sub 1, S sub 2, S sub 3, and S sub 4. So if we're looking at the summation, as k goes from 1 to infinity of k, let's sort of see if we can envision what that refers to. So when k is a 1, the formula is k, so you just have 1, but we're adding these up as we go. When k is a 2, then you'd be adding a 2. When k is a 3, you'd be adding a 3, etc. So the first 4 partial sums here then, S sub 1 would be the first one of those, just adding the first term, which is a 1. I guess I want to change color. S sub 2 would be the sum of the first 2 of those. So that's 1 plus 2, which gives me 3. S sub 3 would be the first 3 of those, which would be added, which would be 6. So S sub 4 would be the sum of the first 3, which was 6, plus the 4th term, which is a 4, would give me 10. So this is a very easy calculation, but we're pretty deep in the notation now, and it's easy to get confused. So are there questions about how we would use the written infinite series to come up with the first 4 partial sums?
I have a question.
Yes, ma'am.
So, or can you just explain again how you got S1, S2, like what you were adding up?
Yes. So a partial sum means you add up the terms of the sequence up to a certain place. So S sub 1 says add up the first term of the sequence. S sub 2 says add up the first 2 terms of the sequence. S sub 3 says add up the first 3 terms of the sequence. So if we look at the sequence up here in green, then S sub 1 is just the 1. S sub 2 is the 1 plus the 2. S sub 3 is the 1 plus the 2 plus the 3.
Yeah, that makes sense.
Because you're adding up the first 3 terms. Is that okay?
Yes.
Think of it this way. What we're trying to do is what I've written as a little formula in green. And if I'm adding these numbers just myself, I would just add them from left to right, and I would kind of keep a running total as I go. So I'd say, okay, I'm going to just add up numbers, 1, 2, 3, 4, 5, up to whatever. So 1 plus 2 is 3. That's when I get the first 2. Plus 3 is 6. Plus 4 is 10. Plus 5 is 15. I would kind of keep a running total as I go. The partial sums is that running total. It's basically S sub 4 is what are the first 4 terms added up. S sub 5 would be, well, what if you then add the 5th one to that, etc. How does that sound?
Yes, that helps.
Okay. Yeah, so like I said, it's actually not a challenging concept, but the notation is just getting pretty deep here with the subscripts and the curly brackets and the vocabulary. Yeah, it's overwhelming. Okay, so then it says for part B to try to estimate the limit or state that the limit doesn't exist. And so for S sub n, that would be basically like saying if we keep added these up and you went off toward infinity, would you settle in toward a value or would you not? If you settle in toward a value, that would be a limiting value. Or if it doesn't settle on a value, then it doesn't exist. So what do we think is the case here? So I see, can we make a formula for S sub n was a comment Marcus made, but of course I don't know how quickly I responded to that. Was that for this, Marcus? You could type in if possible. Is that for this example we have here, or are you thinking for a different problem from earlier? Was that the one where we were doing the 0.9s? Is that the one with the 0.9s? Like where we were adding a 9 in a decimal that extended? Yeah. So yes, we're gonna, I held off in trying to make a formula at this point since we are in the sort of the overview in 8.1. And I thought we'd talk a little bit more about formulas when we get to 8.2 and 8.3, both for sequences and series, because we have bunch of formula stuff that we do in those sections. So even though we could still try to come up with a formula at this point at the introductory level, I just thought it was pushing the problem a little too far, and they don't emphasize that too much in this first overview section, but we will be doing that more in 8.2 and 8.3. So I'll ask you to hold off for a little bit. Thanks for your question. Sorry I didn't see it sooner. I'm trying to juggle several things here. Okay. Well, what's going on here, and again, we can kind of just sort of discuss this with the basic idea, is that the thing that we're adding is just going to be larger and larger and larger, right? Literally, the number that's added to the next term is the sequence, is the next integer value. So eventually you're adding 100, then you're adding 1,000,000, then you're adding 1,000,000,000. And so in this simple example, since the numbers just grow and grow and grow, the sum of those numbers as we go out also is just getting larger and larger and would not settle in on a value. And so we'd have to conclude that in this case, it's a DNE. Whoops, let's try to change that. I may have reached the limit of my ability to go down. Let's see. Oh no, there we go. So for part B, it says to determine if there's a limit. So in this case, the limit as n tends to infinity of S sub n does not exist. Is that something that we can see, or has it gotten too confusing to draw that conclusion? Comments, suggestions, questions?
Wait, so how did you come up with that conclusion?
Well, one of the ways is to look at the pattern. So if you look at S1, S2, S3, S4, you're seeing that the number just keeps growing and growing and growing. 1, 3, 6, 10, and that the next one would be 15, 21, that it just, and you're literally looking at the fact that you're just adding a larger and larger number. Now, we don't have a formula for any of these right now for S sub 1 or S sub 2 or S sub n, other than the summation in the beginning. So it ends up being a question about, they're basically asking us to determine if this has a value. And as we are adding numbers, eventually, if you kept going, you'd be adding 1,000, and you'd be adding, 10 to the 10th power. You're just adding a number. The number that you're adding to the partial sums itself goes to infinity. So if you add all of those up, you definitely get a number that grows without bound. So what I've provided you may be unsatisfactory because it's what we call an analytical argument. And it's not a formula to plug into, but that's the nature of what we're going to be looking at in this chapter, that we're literally looking at things like what I've boxed up in yellow here and trying to say, does this infinite sum settle on a value or not? Does it converge or diverge? Does it have a limiting value, or does that limit not exist? Is that a DNE? Does that make sense or no?
Yeah, that makes a little more sense.
Yes.
Thank you.